Hello everyone, myself Rupam Das, Assistant Professor of Asansol Engineering College in Electronics and Communication Engineering Department. This is my third lecture. Name of the subject is Signals and System. Learning outcomes are at the end of the session, student will be able to understand various operation of signals. Contents are amplitude scaling, addition of the signal, subtraction of the signal, multiplication of the signal, even and odd part detection, differentiation, integration, time shifting, time scaling, and time reversal. These are the reference book. First book is Signals and System by Anand Kumar. Second book is Signals and System by Torun Kumar Rawat. Third book is Signals and System by Ramesh Babu. Fourth book is Signals and System by A. Nagor Kani. Operation of the signal. The independent variables for a continuous time signal is time t and for a discrete time signal is n. The transformation of signal is the central important concept of the signals and system analysis. Transformation of independent variable involves simple modification of t and n. Some of the important transformation of independent variables are time shifting, time scaling, folding, or time reversal. And in this section we are going to discuss about the this some of the useful signal operation. Some of the useful signal operations are amplitude scaling, addition and subtraction, multiplication, time scaling, and also time shifting. So the amplitude scaling of a continuous time signal, one signal is been given to you. Suppose ut is my original signal, and if I'm going to amplitude scaling, and it is been to be done yt is equal to 2 into ut, so that means 2 is multiplied by the ut, so the signal amplitude is going to increase. Now if I'm going to multiply it with help of minus of 1, so that means its value is going to be decreased. Now if I'm going to divide it by 0.5 into ut, so it can be 0.5. This type of signal we are going to obtain. This is known as amplitude scaling of continuous time signal. Next, amplitude scaling for discrete time signal. Now original signal has been given un is equal to 0 comma 0 dot dot 1 1 1 and 1. Now amplitude is going to be scaled with the help of this particular expression. Yn is equal to u 2 into un, so that means its value is coming 0 comma 0 2 comma 2 comma 2 like this. So this is the graphical representation where un is been written like this, and if I'm going to multiply it with the help of 2, so this particular signal can be obtained. Next is addition of the two signal. Let's the two signal to be added by x1t and x2t, then their addition is given by yt is equal to x1t plus x2t. Now let us assume x1t is equal to ut and x2t is equal to rt, unit step function and ramp function. Suppose we want to obtain yt is equal to x1t plus x2t, that means yt is equal to ut plus rt. This operation is performed by the following. Here ut is equal to unit step function, that is equal to 1 for t is equal to 0 to infinity, and rt is equal to unit ramp, so that is equal to t for t equal to 0 to infinity. The addition is shown in the tabular form in the table, and also in the graphically it can be obtained like this. So here in the tabulation form the signal is going to be represented. Here x1t is equal to ut, that is the unit step function, and x2t is equal to rt, this is the unit ramp function. Now here if I'm going to add x1t plus x2t, so that means as per the position value of the signal, its signal is going to be added. So at position 0 its value is 1, and at position this in the second case at position 0 its value is 0. So 0 plus 1, that is equal to 1. Like in that way, if I'm going to for position number 1, its value is equal to 1 and its value is again equal to 1, so 1 plus 1, that is equal to 2. So like in that manner the addition of the signal can be constructed, and this is the graphical representation of the addition of the signal. Now next is discrete time signal in addition domain. So here the position value for first signal x1 n, that is equal to un, this value has been written, and x2n second value is been written like this. Now if I'm going to add these two signal, as per the position value is been concerned, its value is going to be added. So that means at position -2 its value is 0, but here in the second case at position -2 its value is equal to -2. So depending on that, this value is going to be -2. Like in the same manner, at position -1 its value is equal to 0, and in the second case at position -1 its value is equal to -1. So if I'm going to add these two signal, so its value is coming -1. So like in that way we can add these two signal, and its corresponding representation of the signal can be obtained like this. Next, the subtraction of the continuous time signal. Now again same procedure is going to be obtained over here. One unit ramp function has been written over here, and unit step function is like this. As per the position value, if I'm going to subtract these two signal, the final representation of the signal will be obtained like this. Next we proceed subtraction of the discrete time signal. So one discrete time signal x1n, its value is been written over here, and x2n another type of signal, it's to be written over here. And if I'm going to subtract x1n minus x2n, so x1n value is equal to 0, but x2n value is equal to 1. So 0 minus 1, that is -1 should be written over here. At position 1 its value is equal to 1, and at x, in case of x2 at position 1 is again its value is equal to 1. So that means if I'm going to subtract these two signal, so that means 1 minus 1, that is equal to 0. So like in that way this particular signal can be constructed, and for all the position value this subtraction operation is going on, and finally we can construct this particular signal. Next, multiplication in terms of continuous domain. So in case of continuous domain, two signal is again written, x1t that should be written like this, and x2t is to be written like this. These are the two signal. Now if I am again going to multiply as per the position value 0, its again value, it's at this point its value is 0, and x2n its position value is 0. So like 0 into 0, that value is equal to 0. Now in the second case, at position 1 its value is equal to 1, and at position 1 for the second case its value is -1. So the -1 into 1, so that is -1. Like this way you can construct the multiplication of continuous domain signal. Next, multiplication of discrete time signal can be constructed. Here in discrete domain, two signal is been written, x1n that is equal to 0, 1, 0, 1, 0, 1. 0 is the central value or central position value, and x2n second signal is been written like this, -2, -1, 0, 1, 2 and 3. And if I'm going to multiply these two signal, so that means first we, according to the position value, its value first written or drawn, first x1n, then x2n value is been written, then as per the position value is been concerned, its value is going to be multiplied, and finally the signal is going to be constructed like this. Next, with determination of the even and odd part. So for the continuous time signal, even part of the signal that should be equal to half of xt plus x of minus t, and odd part of the signal that is equal to half of xt minus x of minus t. So the even and odd component for discrete time signal xn, that can be written in terms of a n. So even part of the signal that is equal to half of xn plus x of minus n, and odd part of the signal can be written x of 0 o odd part of the n, that is equal to half of xn minus of x minus n. So in this way the continuous time even odd part and discrete domain even and odd part can be constructed like this. Next, differentiation operation. If xt is a continuous time signal, then its derivative is given by yt is equal to d dt of xt. For example, an inductor performs differentiation operation. Let the current passing through the inductor, it is denoted by it, and then the voltage across the inductor can be written as vt is equal to inductor, that is L d dt of it. In this way the differentiation operation can be performed. Next is integration operation. Similarly, the integration of xt with respect to time, it is given by yt is equal to integration of minus infinity to t x of tau d tau. So here tau is equal to integration variable. For example, a capacitor performs the integration operation. Now let it is the current which is passing through this capacitor as shown in the figure, and the voltage developed across the capacitor can be written as Vt is equal to 1 divided by C integration minus infinity to t I tau into d tau. So in this way the integration operation is going to be performed. Next, operation performed on independent variable. The independent variable in our discussion is time t or n. So the operation discussed in this section are performed on t or n. If it is in terms of a continuous time signal, so that we can represent the signal like t. If it is discrete domain, so we can represent the total signal in terms of a n. Now we will discuss the following operation in terms of a time shifting, in terms of time scaling, and folding or time inversion. Now first we are going to see time advanced for continuous time signal. Here t position value is been written minus 3. In minus 3 xt value is minus 3. In position value minus 2 its value is minus 2. Then minus 1 0 0 1 1 2 2 3 3. Now so if we are going to time advance the signal, that is x of t plus 2, so that means minus 3 as per the position value. So minus 3 plus of 2, that is x of minus 1, that means minus 1 position value is to be shifted, and this value is coming to like this. Now again for the second case, its position value is minus 2. We are going to time advance the signal for plus of 2, then minus 2 plus 2, that is equal to x0. So that means at position 0 that value should be shifted and it is coming to 0. Like in that way all other position value is going to be shifted, and in terms of that the time advance of continuous time signal can be obtained. And this is the graphical representation for the time advance of a continuous time signal. Next is time advance of for a discrete domain signal. So let xn is equal to un be the original signal, and if I'm going to advance the discrete domain signal x of n plus 3, that is equal to u of n plus 3. Now that can be obtained like this. This is the unit xn original signal. Now if I'm going to advance the total signal with position value of 3, so that means this particular signal is going to be shifted towards this direction, and it can be looking simply like this. The original signal mathematical expression is like this, and after shifting the total operation is going to be obtained like this. So this is the time advance of a discrete time signal. Next is time delay of continuous time signal. Again the t position value is been written. At position minus 1 its value is 0, at position 0 its value is 1, at position 1 it is again 1, at position 2 its value is 1, at position 3 its value is 1, and at position 4 its value is again 1. Now if I'm going to time delay the continuous time signal, is depending on its position value we are going to delay it. So that means x of t minus 1, that is equal to u of t minus 1. So that means at position minus 1 of minus 1, so that means u of minus 2. But here in this case we cannot find the position value of minus 2. So if the position value is not been written, so that means it's to be denoted by 0. Now again next case 0 minus 1, so that means its position value of minus 1, u of minus 1. At position minus 1 its value is 0, so that means 0 is coming and it is shifted and its value is to be 0. Now in the same way the other position value is to be denoted, and we can easily find it out the time delay of a continuous time signal. And this is the original signal, and after time delay this type of signal as per the position value we are going to obtain this type of circuit or signal representation. Next, time delay for discrete domain signal. So in case of time delay of a discrete domain signal, so un, this is the original signal. Now if I'm going to shift it minus 4, so in terms of right side it is going to be shifted to the 4 position, position number 1 2 3, and this particular signal from at position 0 which is 1, it is shifted and it in position number 4, this value of the signal is to be denoted like this. This is the graphical representation, and in terms of a mathematics this can be represented like like this. Next, we are going to proceed time scaling of a continuous time signal. Now, if we are going to scale it, the total time signal, so as per the position value, this value can be written like this. And if I'm going to time scale with it, suppose that in this case we are going to scale it x of 2t. So that means x of 2x minus 2. So its position value is minus 4. So at position minus 4 should not be any value. So that means it is 0. Now if I'm going to multiply it minus 1.5 multiplied by 2, so it is coming minus 3. So again minus 3 values, there should not be any value, so it is again 0. So like in that manner, all the position value is to be identified. And if I'm going to, this is the original signal representation, graphical representation. After multiplication, signal is going to be compressed, and the total signal should be looking like this. Next, we are going to see the signal expansion. For the expansion of the signal, we are going to first represent the total signal in a tabular form at position value. Depending on its position value, the signal original value should be written. Then if I'm going to multiply it with 0.5, so that means 0.5, that means if I'm going to make it in terms of a fraction value, so it is coming half of t. That means simply we are going to divide it. So depending on that, the signal is going to be expanded, and the expanded signal, when we are going to plot it in the graphical form, it simply should be looking like this. Next is time scaling of a discrete time signal. So again, in the discrete domain, whatever the position value, whatever the concept we are going to develop for the continuous time signal, that can be implemented on a discrete domain. So in case of discrete domain, it should be represented by n. So depending on the position value, the value should be written in terms of xn. After that, if I'm going to time scale it, so if so that we can multiply, here in this case I have multiplied x of 2n. So that means minus 4 multiplied by 2, it is coming minus 8. But here in this particular table, minus 8 value should not be, we cannot find that minus 8 value. So depending on that, its value is 0. So again minus 3 multiplied by 2, it is coming minus 6. So but here minus 6 position value is not, we cannot find it. So again it is 0. Then again minus 4. So we have found minus 4. So in minus 4, its value is 0. So that value should be written over here. Now like in that manner, all the value should be evaluated. After evaluation, first we have to draw the original value as per this particular table. And when it is going to be time scaled, that scaled value should be written, and the graphical representation should be simply looking like this. Then on signal expansion, we can expand, like in the continuous time domains, we can expand the signals. Basically we are going to divide the total signal with some value. Suppose this is my position, the position corresponding value should be written. Then on, if I'm going to divide the total signal with half, so that means it should be looking like this. And after graphical representation, the signal can be expanded, and this expansion of the signal in discrete domain, it should be looking like this. Next, folding of the signal, that means we can fold the total signal just like mirror image. This is the positive side value, it's to be written over here. And if I'm going to folding the continuous time signal, its mirror image of the signal should be reflected at after folding of a continuous time signal. Now folding of a discrete time signal, again the signal can be represented in terms of a n. These are the position value, its corresponding xn value should be written over here. Then on, if I'm going to fold in terms of a discrete domain signal, the value which is shown over here, its reverse part, it should be reflected in this particular portion. So that is known as folding of a discrete time domain signal. Next is folding and delay. We have to fold the signal and then we have to delay the signal. So simply, if I'm going to delay the signal of an original signal by k unit, so it can be written x n, that should be delayed by x of n minus k. So folding and delay, so we have to fold the signal. So after folding, it is coming x of minus n, and if I'm going to again delay it, so it can be written x of minus n minus k, so it can be written x of minus n plus of k. So this is the folded version of the signal, and if I'm going to advance it by +2, so it can be written like this. At in front of the +2, the signal is going to be shifted. This is position 0 1 2, so that means that 3 value is coming to the middle section, and all other part are going to be shifted to the positive side. So that is the folding and delayed version of the signal. We can again represent it in terms of a folding and advanced. So before going to do this, if I'm going to simply advance the total signal, so that means it can be written xn, that is equal to x of n plus k. So if I'm going to fold it, so it can be written x of minus n, and after the advance of the signal, so it can be written x of minus under bracket n plus k. So after solution, it is coming x of minus n and minus k. So that previous, in this previous example, the original signal is going to be advanced, but here delayed. But in this case it is going to be advanced, that means it's simply shifted to this particular side, and folding an advanced version of the signal can be obtained. After that, this is the original signal. Some depending on this particular concept, we can make some mathematical question. Suppose xt is this particular value is equal to 1, and it is written -1 of 2 plus 1, and it is 0 otherwise. Now if I'm going to multiply xt into del t, so that means it can be written, xt value should be written first, then on if I'm going to multiply it with del t, so that is the original signal xt, this is the del t, that means delta function. If I'm going to multiply it, the original signal should not be any type of changes, so this same function we can obtain it. After that, if I'm going to delete the signal, then we have to advance it. The signal should be looking like this. If I'm going to advance the total signal, so signal can be obtained like this as per our previous concept. And after that, if I'm going to again represent the advanced version of the signal, then if I'm going to multiply it, so if you see, after advanced version of the signal, it should be looking like this, and this is the unit step function. So at this position it doesn't have any value, so at this position this value is 0, and positive side also there should not be any value. This position value is 0, and this position value is 1. So basically we are not finding any value, so that means it can be written equal to yt is equal to 0. So this, in this way we can obtain it. And up to this I am concluding my today's lecture, up to the session lecture, and thank you.